Now, once again, if we're looking at the parabola x squared equals to 4ay, okay, and let's say I've got the point P, once again, somewhere over here, and let's say that it's given by 2ap squared, the standard parametric representation of the standard parabola. Say what I want to do now is I want to find the equation of the tangent at the point P, okay, the equation of the tangent. Now, if we want to find the equation of the tangent at P, we need to know what the gradient of the curve is at this particular point. And after I found the gradient of the curve at that point, then of course I can just say that the equation of the tangent is given by y minus y1 is equals to m times x minus x1. So when we want to find the gradient of the curve, okay, at this particular point, we don't need to, I mean, it's one potential way, but we don't need to take x squared equals to 4ay. Okay, some people take this equation, they rearrange it as y is equals to x squared over 4a, right? And then they differentiate that before substituting the coordinates of p into dy dx. Now, there's a far simpler method. Okay, we call this parametric differentiation. And the idea is that at the point P, right, where x equals to 2ap and y is equals to ap squared, what we can actually say is that dy dx is equals to differentiate the y with respect to the parameter p over differentiate x with respect to p. Now, this is essentially chain rule rearranged, because if we think about dy dp divided by dx dp, this is the same as saying dy dp times dp dx, right? So if we have dy dp times dp dx, that's chain rule for dy dx. And if we recognize this, it actually becomes very easy to apply as well, because y is equals to ap squared. So if I differentiate ap squared, that's actually just going to give us 2ap, right? Because if I differentiate ap squared, a is a constant, p squared, take the 2 in the power down to the front and subtract 1 away from the power, and then over dx dp, x equals to 2ap. So if I'm differentiating x with respect to p, I'm just going to get 2a, which is the constant in front of p, right? So it's 2ap divided by 2a. The 2a's cancel out, which means that the gradient of the curve at that particular point is therefore p. So once we've got this gradient, we can now say that the tangent at p, okay, the tangent at p is given by y minus y1 is equals to the gradient times x minus x1. And if I expand the whole lot, we're looking at y minus ap squared is equals to px minus 2ap squared. Moving the minus ap squared from the left to the right, okay, this is now going to give us y is equals to px minus ap squared. And this is the standard equation of the tangent, okay, the standard parametric equation of the tangent, okay, for the point P on the parabola, x squared equals to 4ay. And just like the parametric equation of the chord, we need to make sure that we know how to prove this, okay, because for one, it's standard bookwork, and two, in 99% of the times, questions in the exam would actually need us to prove this. Okay, the only times that we don't need to prove this is when the question gives us the equation of the tangent and then it tells us that we don't need to prove it explicitly, or if the question asks us to simply write it down. Okay, in all other scenarios, whenever we need the equation of the tangent at P, we need to make sure to chuck this proof here. Now, just before I leave it here, okay, some of us might actually realize that there's a very clear-cut relationship between the equation of the tangent versus the equation of the chord. So according to what we've just got, okay, the parametric equation of the tangent is given by y is equals to px minus ap squared, whereas earlier we said that the parametric equation of the chord is y is equals to half p plus q times x minus apq. So here, if I introduce in another point for q, okay, let's say that point q is somewhere over here on the parabola, right? And this is going to be q given by 2aq, comma, aq squared. So what happens is that if we take this chord over here, okay, let's say p is fixed over here and q is free to move anywhere it wants. So if I move q closer and closer to p, what you guys will realize is that the chord is actually going to slowly approach that of the tangent. Okay, and the closer that q gets towards p, the more like the tangent the chord becomes. Okay, so what we say is that the tangent is pretty much the limiting position of the chord. Okay, so the tangent is pretty much the limit as the parameter q approaches p. That's just saying that the point q is getting closer and closer to p, right, for the equation of my chord. And if we take this limit, right, my equation of the chord is right here. If I say, okay, let's let q approach p, then you guys can see that the equation of the chord becomes half brackets p plus p times x minus ap times q, but as q gets closer to p, that's going to be ap times p. And what this equation becomes, right, half times 2p is just going to be p times x minus ap times p, that's ap squared. So the chord does become the tangent when the second point draws closer and closer to my first point here. Okay, and this is essentially the idea behind first principle of differentiation, if you guys remember, back from year 11 to math. So I thought I'll just point that out. Okay, so anyways, that being said, make sure you guys know how to prove the standard parametric equation of the tangent. Okay, so that being said, this is what we have for the parametric equation of the tangent.